Hello everybody. So today what I'm going to do is write a binary search function and use it in Python. So a binary search algorithm used with Python is something which you would probably come across on a computer science course and or an interview question maybe. So it's always worth knowing something like this, and what I'm going to do is quickly explain what it is. So we've got a variable which we'll call nums, which is a Python list or an array if you're doing it in C or JavaScript or whatever. So it's a sorted list. So let's go for 1, 3, 5, 7, 9, and then throw in a few different numbers. How many is that? That'll do. That's 8. Because what I probably will do is debug this, so I don't want to make it too big. We've got a list of 8 numbers. What we want to do is find the index of a target number. So I'm going to write my code and I'm going to say find me the index of number 15, and we know from looking at it that it is going to be 0, 1, 2, 3, 4, 5. Or if you do it the other way around, what we could do is say find me the item that is at index 5. So what we'll do is we'll start a function, def binary search nums and target. Actually, we want to return an int, don't we? I'm also just going to, if you've not used this before, this is from typing import list is type checking. So what I can say here is nums, and then we can make sure that it checks whether it's a list, and we'll check that the target is an int. So far so good. We're going to create a low variable which will represent the integer of the index of the first element in the array, and we'll do the other end. So high will be the length of the array, that will be 8, but because we're starting at 0, we want to go from 0, we want to go one less than that. You'll see why in a minute. Because otherwise we'd be going from 0 to 8, which would be, we'd get a list index out of range error. Good. Okay, so what we're going to do is we're going to look at the array. We're going to find the midpoint. If it's an even number, it actually will be going to the left. If it's an odd number, you would find the odd number, which would be your middle. So while low equal to target, we're going to keep iterating through a while loop until effectively low and high both equal our target, because we're going to keep chopping the list in half and getting closer and closer to our target until we hit our target, and then high and low will both equal the target. So we could use low or high. We're going to say, well, put a 0 in there, didn't I? While low is not equal to the target, then we are going to iterate through, and we will say if target, so that's the number we're searching for, the number of the index, So we're going to search. We want to say we're going to pass it. The target is typically going to be something like 3. If the target is 3, then we want the function would return that, which is 0, 1, 2, 3. So we'd want it to return 7. So what we'll say here is if target equals, again we can say low, then return we need to create a variable to store the midpoint. So we say mid equals, so to start with, mid is going to be high plus low divided by 2. But we use a double / so that it gives us an int, so it will round it down. So if we run this and the target was, no, we want to say if the target is low. So the first time we run it, if the target is low, correction, if the target is equal to nums mid, then return mid. So do we say if a target, which the target is, say for instance 7, and then we say if the target 7 equals nums mid, which would be, will it be 7 or will it be 9? We'll find out when we test it. Then it would exit the while condition. So then we'll say else. No, we do Alif. If target is less than nums mid, that means the target is on the left hand side of the center. So then we want to, low will stay as low, but high we would reduce to being the halfway point minus 1, which becomes high equals mid minus 1, and then the opposite for low. So low would be mid plus 1, because if the target, if it's less than the, if the target is less than the midway point, high moves to become the halfway point minus 1, or if the opposite is true, then low moves up and then it becomes midpoint plus 1. So low is just past halfway and high is at the top. We're going to test this any second. Return minus 1. So let's do def main. Returns int. X equals binary search, and we'll pass it nums, and we'll pass it, I know I've been saying 7, let's pass it 15. And then we want to print X, and then if name equals thunder main, then run main. Just going to format this. This looks pretty good. I'll put in a doc string just to keep the linter happy. Find the index of the target int. Right, okay, if you're ready, let's test this and see if it works. And I've not even saved it, and it's got a really strange file name. Let's just in search.py. Okay, let's run it. And it worked first time. It looks like viewers, it looks like I've remembered how to write a binary search. So what did I say? If what did I say? Practice makes perfect. There we go. So now we know, now we can see it working. I'll I'll debug it. So we'll pass it another number as well. So let's give it the number 3. And again, you could write an automated test for this, and you could pass it all sorts of values. So yeah, ran it again, and it returned 1. You see that there, just above the blue. There we go, 1. So if I pass it 3, it gives me the index 1. So let's try and confuse it, and let's just say 9. This is pretty tried and tested algorithm, so I don't think we can really break it. There you go, 4. So 9 is at position 4. So it's 0, 1, 2, 3, 4. So that's correct. This is probably easier doing in Python than, say, C. Well, it's for me anyway. I don't know what else doing there. Go. Just notice you've got the double. So if we took that out, let's see if it still works. No, you see it gives us a float. So just things to watch out for. You need the double / there so that you can get an int. And the other thing to watch out for is on line 9. Do you see the -1? If we didn't have the -1 there, I'll run it again, we'd probably get a list index out of range. Oh, we didn't. That's interesting. Let me just try one more number. Let's try 15. Yeah. 15. That gives us 5. Is that correct? 1, 0, 1, 2, 3, 4, 5. And just try it with 19. That actually seems to work. I don't know what. Yeah, so that's 7. So is that giving us wrong numbers? 19. 0, 1, 2, 3, 4, 5, 6, 7. Okay, so if you start at 0, that will give you 7. It depends whether you want to. You could. Depends whether you want to start at 0 or not. If you do that, so then 1 would be position 1. We'll run that again, and that's still 7. So yeah, it looks like it works either way. One other thing to change is low. You could say high there, and I think it will still work. Yeah, because when you keep chopping the array in half, you keep getting closer and closer to the number you want, and eventually high and low both equal your target. So or high not equal to target. Eventually high equals the target and low equals the target, and they equal the target on the same pass. So let's run the debugger. There's probably tutorials on on YouTube. Sorry, it's been a long day. Excuse my what is it they say? Muddled. What? It's a spoonerism, isn't it? If you don't know what spoonerism, look it up. It's where you get the first letter of each of two words swapped around. It can lead to all sorts of errors. Right, so let's go. We've got high on our first. In actual fact, that's why it didn't matter, because our 2 forward slashes are just rounding everything down. I'm going to stop that and set it back how it was. Low should equal 0, and we'll do length and nums. And what we will do is keep an eye on the variables in the top right hand corner, and to begin with, high equals that's what I wanted to do. High should be length and nums -1, not +1. It still works, but it's not correct. Okay, so low equals 0, high equals 7, mid equals 3. So what it's done is it's gone high plus low, which is 0 plus 7. If you'd done it the other way, you could have done, if you'd said low equals 1, 1 plus 7 would give you 8, divided by 2 would give you 4. It actually makes no difference because you're subtracting 1 here anyway. You're moving the midpoint left or right, but let's keep going anyway. If target is less than nums mid, so mid is 3, so 0, 1, 2, 3. So if the target, which is 19, is less than 7, so it's going to skip that, then it will carry out this line 20. So low equals mid plus 1. So now the low end will equal 4 and high will equal 7. And then what we'll do is we'll find the midpoint between those two. And then we will check if the target, let's go. We're checking now with low is 4, mid equals 5, high equals 7. So it's going to skip line 15, 16. Now it's going to say, is the target 19 less than the, what's it, index number 5, which is not. So again, it's going to go down to line 20. And now low, low moves up to the midpoint plus 1. So low's now going to move up to position 6. There we go, you see position 6. And then high plus low is going to be 13 divided by 2, which would be 6.5. It rounds it down, so it's going to give us 6. So mid will become 6. Yep. And position 6, does position 6 equal the number? No. So then it's going to say, it's going to go down to line 17. And then it's going to say, is the target less? So it's still less. So it's going to go to line 20. And then low equals mid plus 1. So it's going to be 6 plus 1, which is 7. And now it's going to go and say, is position 7, so it's 0, 1, 2, 3, 4, 5, 6, 7. Now it should say mid equals high plus low is 7 plus 7, 14, divided by 2 is 7. So if target 19 equals, there we go, equals nums 7, then return mid. So we'll get a return on this attempt, and we'll break out of the loop. And there we go. That gives us a print, and then it prints it down here, which gives us 7. So we were trying to check where 19 appeared in this list. So binary sort, not a binary sort, a binary search. If you were searching for that from left to right, that would take you you'd find it on the 8th attempt. But by doing it this way, we chopped it in 2, chopped it in 2, chopped it in 2. So I think we found this on the 4th attempt. We could actually put in something to measure that. But if you're looking at efficiency of your code, naught n code. Efficiency. Big O notation. Sorry, I forgot. So the big O notation is, if you do any of the LeetCode examples, it calculates the time complexity, as you can see. So I'm not going to talk about this because you don't really want me to read all this off the screen, and it's not something I know in depth anyway, but I'm aware of it. So when you are writing code, think, for instance, whether you have to iterate through every element in an array, or whether you could chop the array in half and then find something in the right half or the left half. So that's the whole purpose of the binary search. Wikipedia binary search. And whatever your language is, you could write this in C, C++, Java, JavaScript, so on. Also known as half interval search, logarithmic search, or binary chop. In a search algorithm that finds the position of a target value within the sorted array, binary search compares the target value of the middle element of the array. If they are not equal, the half which the target cannot lie is eliminated, and search continues on the remaining half, again taking the middle element to compare to the target value, and repeating this until the target value is found. If the search ends with the remaining half being empty, the target is not in the array. So there we go. Worst case performance, 0 log n. Best case, 0, 1m. So big O notation. When you do any problems on LeetCode, it may often specify which of the big O notations you should be aiming for. As you do more iterations, if you have, for instance, a for loop inside a for loop, then you start going up into, I can't remember, is it the quadratic for a for loop inside a for loop? I can't remember, but yeah, bubble sort. So if you look at a bubble sort, that could typically be O n squared. It's not a very efficient way of sorting. It's probably the way. More efficient algorithms such as quick sort. Quick sort built into languages such as Python, or so there you worst case performance, best case, so on. I'm going to leave it there. hopefully if you've not come across big O notation before or bubble sort, then I've given you some some inspiration. If you already know it, then you probably know it better than me, and I'm not going to pretend I'm an expert on it. So there we go. Binary search. That's one solution. I'm not saying it's the only solution. If you can do it another way, then let me know, drop a comment and all that stuff. So subscribe, thumbs up, and I don't know, what was it? Hit the bell for notifications. And yeah, well, thanks for watching anyway. So yeah, see you next time.